Bem-vindos to one more episode of the Type Theory for All podcast. As always, this is your host, Pedro Abreu, and today I have the great pleasure to interview David MacQueen. He has worked at Bell Labs for around 20 years during its golden age. He's a professor at Chicago University for more than 23 years. He is one of the co-designers of SML and one of the fathers of the whole programming language, the one that introduced the notion of algebraic data types. And if you guys know me, you know that I'm really excited about algebraic data types. My master's was related to that topic, so this conversation is very special to me. You know, just talking about how these things came to be, what was going on historically speaking. He just has so much story, so much to tell us. It was a great pleasure to talk to him, and it's my great pleasure and honor to share it with you all. But before we dive into today's interview, a few quick messages for you. And this is the Type Theory for All podcast, a free and completely open platform to educate and document the history of type theory, theorem provers, formal methods, and programming languages at large. To support our commitment to free access to knowledge, consider donating any amount to our Ko-Fi platforms. Simply go to our website, typetheoryforall.com, and follow the prompts. Any amount will be of great support to our cause. And a great shout out to Andrew and Bruno that took the front into organizing a Cox study group in 2024 at Discord, and now in 2025 they're going into Quick Check. Another huge shout out to Jan Tusho, who organized a separation logic study group. So if you'd like to be a part of a growing community in type theory and related topics, please consider joining our Discord. We are currently looking for community leaders that are willing to organize other study groups for 2025. So without further ado, let's get into this episode. All right. Welcome, everyone, to one more episode of the Type Theory for All podcast. I'm extremely excited to be here today with David MacQueen. Did I say your name correctly?
Yeah, roughly. MacQueen.
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 Well, MacQueen. That's the hard part of being a foreigner. English is not my native language. I'm always butchering people's names, but hopefully people don't get too mad on me. So here's a good place that I thought about we could start. One thing that I've noticed when I was doing my master's in the US is that there was a little bit of, the way that computer science and programming languages developed to nowadays, there is quite a difference between how things were in computer science birth, because, computer science was born out of mathematics. So I think the right place for us to start this conversation, since you did your bachelor's in mathematics in Stanford, and then you went into recursion theory, like more computational side of things through your PhD. I would like you to start by telling us this story of how you were in mathematics and how did you get into computer science per se from there.
So I did a pretty conventional mathematics undergraduate degree at Stanford. There was a logic course that was taught by Dana Scott in the philosophy department that I would have liked to have taken, but it conflicted with rugby practice in the winter quarter. So I never got around to taking Scott's logic course, which was a shame.
Well, priorities.
Anyway, I went to MIT and I wasn't entirely decided about whether to do a thesis in computer science or mathematics. I was in the mathematics department, but the mathematics department had an applied math program that was connected with computer science, which is part of the electrical engineering department. And so there were several people who did PhDs in computer science as part of the applied mathematics track in the mathematics department. But I was taking courses in logic and trying to take Joel Moses's course on Lisp at the same time, and it was conflicting, I think, with set theory or something that I wanted to take. And so at some point fairly early in my first term, I had to make a decision, and I decided on logic. And then, so I continued and worked in what is now called computability theory. In those days, it was called recursion theory. That was the old name for the study of computability. And I did a thesis in that area on a topic which is sort of a generalization of a fundamental result in the study of degrees of unsolvability. My thesis work at MIT in logic was about a kind of generalization of a fundamental result in the degrees of unsolvability to computation or computable functions of higher types, which is functions that operate on functions and produce functions and so on. And then I had an obligation to go into the Air Force because this was the Vietnam War era, and I was in the ROTC at Stanford. And so I got a deferment to do graduate work at MIT, and then had to go into the Air Force directly after MIT, where I taught mathematics at something called the Air Force Institute of Technology at Wright-Patterson Air Force Base in Ohio. So that was fairly mild. I was teaching basically applied mathematics to engineering students of various kinds, who were all Air Force officers, including one astronaut. So that was interesting. So I spent almost 3 years in the Air Force, and then getting out of the Air Force, I had a kind of choice as to whether to look for jobs in mathematics following the kind of obvious traditional mathematical path. And so I applied to some mathematics departments, and I was also interested in getting into computer science. And so I had a contact from MIT, Mike Patterson, who was a professor at Warwick University in England. And I wrote to him and asked him if he had any jobs or knew of any openings in Britain. And he wrote back and said that Rod Burstall in Edinburgh had an opening. So I wrote to Rod and sent him my resume, and he called me up a few days later, and we had a conversation, and he offered me the job. So I decided to go to Edinburgh. And I didn't know a whole lot about computer science. I had taken the two computer science courses at Stanford that were offered to undergraduates. At that time, there was no computer science department, nor was there a computer science undergraduate degree. So I decided to launch off in an unknown direction and go to Edinburgh, and that turned into a very good choice and a kind of turning point in my career. So I'm sort of leaping ahead, but anyway. So that basically determined the future course. Otherwise, I would have gone perhaps to an instructorship at the University of Chicago, or perhaps to a visiting or temporary position at the Institute for Advanced Study.
So if I understood correctly, during your bachelor's, you in mathematics were already introduced to computer science ideas in the formal side and these more logical foundations of computer science?
Not really in my undergraduate courses. Mm-hmm. I took things like, modern algebra, linear algebra, differential equations, real analysis.
Regular mathematics stuff. Mm-hmm.
Etc. You pick up fundamental things like basics of set theory and so on, because that's kind of universal requirements. But so, as I said, I missed taking Dana Scott's logic course, which was taught in the philosophy department. That's true in the field of logic. There were some universities where the logicians were in the math department, and at Stanford there was at least one logician, Solomon Pfefferman, who was in the math department, and of course there was Paul Cohen, who got the Fields Medal largely for his proof of the independence of the continuum hypothesis, which is a really big result in set theory.
Yeah.
And but I didn't take courses from any of the logicians at Stanford.
So then you started doing your PhD at MIT. How did you get into recursion theory, more precisely? What's the story there?
Well, there was a person on the faculty, Hartley Rogers, and he was a very nice guy, a very good teacher, and he had written the sort of standard textbook on recursion theory that everybody used. And so I took his course on recursion theory, and it was a very good course, and I enjoyed it. And so I continued in that field. I also took courses in just plain logic and set theory and model theory, which are, mathematical models of logical theories. The one branch of mathematical logic that wasn't represented at MIT was proof theory, which is a rather technical area of rather abstract views of proofs. And turns out that I did audit a course on proof theory by Hilary Putnam at Harvard, who was teaching at Harvard. So I got a little taste of proof theory as well. But it's not what you would consider proof theory, nor anything having to do with things like proof assistance and automatic proof programs. It's more like what can you prove if you have access to transfinite ordinals and things of that sort.
Mm-hmm. This sounds really exciting because you were there when these topics were kind of in its dawn. Like people were excited and these were developing fields.
Well, not quite. Logic, of course, goes back to Frege around 1879. And then there was Cantor, basic ideas of set theory. And then there was Russell and Whitehead, Principia, and Hilbert's program. And finally, there was Gödel, who sort of crashed everything by proving the incompleteness theorem around 1930. So logic's formalization, or logic's period of formation, definition of the subject was really from the late 19th century through 1930, 40, etc. And for computability theory, kind of the initial big result in computability theory was the unsolvability of the halting problem by Turing. Actually, Turing and Church independently and more or less simultaneously, 1935. And after the discovery of uncomputable things, like the halting problem, there was a technical development of the theory of computability, which was really the theory of incomputability. The computable functions regarded as trivial. If you could compute it, it's level 0. And the halting problem is level 1, or zero jump, it's called, technically. And then you start asking questions like, once you have the halting problem, you can do the halting problem relative to the halting problem to get another level of unsolvability. And you can then do the halting problem with respect to that, and you get another level, et cetera, et cetera. So you can build an infinite chain of more and more unsolvable sets, sets that are not computable and are very hard to compute. So the question, one of the fundamental questions was, is that a linear chain, or is the partial ordering a more interesting ordering? Are there incomparable degrees of unsolvability? So a degree of unsolvability is just a bunch of sets of integers that are computable relative to each other. And you have an ordering. A is computable relative to, or B is computable relative to A, so B is larger than A, or reducible to A, and then out of that order comes an equivalence relation, and the equivalence classes of that equivalence relation are the degrees of unsolvability. So they're basically sets of integers, or natural numbers. So that's the scene. And then around 55, 56, Friedberg and Muchnick, two logicians, discovered a way of building two incomparable degrees of unsolvability. That problem was originally posed probably in the 1940s by Emil Post. So it's called Post's problem in the field. Anyway, so the fundamental architecture of the field, the fundamental questions and definitions and so on were developed in the starting around 1930 through the 30s and 40s and into the mid-50s. So I started my PhD studies in 1968. So it was like an academic generation. I regard an academic generation as on the order of 12 to 15 years. It's typically one's PhD advisors, maybe 12 to 15 years older than you. So I was about a generation beyond these formation years for the subject. And at that point, you start asking kind of secondary questions, not primary questions. And the definitions, well, in fact, the definitions weren't entirely set because my thesis problem was Post's problem for recursion in higher types. So you can, normal recursion or computability is about natural numbers. What functions over the natural numbers are computable? No data structures, just numbers. And if you need data structures, you Gödelize them. That is, you encode them as a number. So you can generalize that to talk about computing when some of your inputs are functions, computing relative to inputs that are functions, and perhaps computing a function as a result. So that's going into higher types. And so then there's a question of what the model of computation is for the higher types. And my thesis was based on a couple papers by Stephen Kleene in the late 50s, where he gave his definition of what computability relative to, at higher types was. Turns out that was a kind of artificial and wrong definition. So in some sense, my thesis was all based on the wrong definition of computability at higher types.
I thought you were going to say you fixed it.
Well, I came to realize it because kind of completely parallel to this. Well, first there was a thesis by Richard Platek at Cornell. He wrote a very famous and very successful PhD thesis where he studied two models of computability, one at higher transfinite ordinals, computing on an ordinal instead of the natural numbers. So you're dealing with infinity there in the sense that some of your numbers are transfinite numbers. And the other thing he did in the same thesis was computability at higher types, using a model that was quite different from Kleene's model. And Platek's thesis, or Platek's model of computability at higher types, inspired Dana Scott, who had been trying hard to find a mathematical model of the lambda calculus, a mathematical semantics for the lambda calculus, but had failed initially. But inspired by Platek's model, he came up with the domain idea and domain theory and associated models of the lambda calculus and so on. And so Playdick's model, or Scott's formulation of it in domain theory, would have been the right model to do what my thesis project was about. But it was too late for me to. Anyway, so a lot of people were doing theses, so I mentioned this result in the 50s, that there were two incomparable degrees of unsolvability. So people went to town on refinements of that result, and what kind of order structures could you map into the degrees of unsolvability? And was it wide? How wide was it? Et cetera, et cetera. How wide? How deep? Essentially, you could take virtually any ordering structure and find a way of mapping it into the. So it was discovered that the degrees of unsolvability had a very rich order structure, and there were lots and lots of technical results and difficult and tricky proof methods to produce these results. But they were only of interest to the inner community, and they were mainly, you got credit for the cleverness of your proof technique. So the result, only 3 people would be interested in the result, but their proof technique might impress people. And in some cases, the proof technique would lead to whole family results. There were finite injury models, which was the original Friedenberg-Muchnick idea, and then there were infinite injury models or methods, which made my advisor's career, and so on and so on. And then in set theory, there were things like Paul Cohen's forcing idea, which was used in the continuum result.
I have a question. Might be a little silly, but it's hard for me to get my head around this. As you've mentioned, there was a lot of effort, and as you said, the modeling techniques that you were using turned out to be kind of wrong. So Dennis Scott put a lot of effort into trying to figure out what is the proper model of lambda calculus, and kept kind of like striking him back. But my question is a little more philosophical than that. Is, why do we care about models of computation? Doesn't computation itself suffice for doing what we want to do? Why do we want to do models?
Well, basically, as a mathematician, one wants to have an abstraction. In other words, there's certain, if you take a particular model like, say, Turing machines, that's what one would call an operational model. It's an actual, at least intellectual device, potentially even implementable in hardware. But if you want to prove something general about computable functions or something like that, the Turing machine has a bunch of kind of artificial, possibly irrelevant features that you have to deal with when reasoning about it.
Right.
So you try to simplify and abstract.
Okay.
Of course, in computability theory, by the time I did my thesis, through the technique of Gödelization, which is encoding non-trivial structures into simple natural numbers, everything was just a natural number, like a Turing machine would be a natural number. So there's Turing machine 537, and that's the starting point. Right. Because they're finite things. You can always just find some way of ordering them in some linear fashion, and it's a discrete ordering, and so you can map it to the natural numbers and so on. And there's some interesting idea, but can you go beyond the natural numbers in some way? But for everything up to the mid to late 60s, the natural numbers were enough to encompass everything you wanted to know. And of course, Scott had kind of ad hoc constructs for the model of the lambda calculus, the D infinity model that he developed. But soon after that, he discovered that there was a kind of universal model, which is P omega, or the power set of the natural numbers, and everything could be encoded. Everything you needed for modeling the lambda calculus could be encoded in that universal model.
Right.
So it went from simple, for that case, it went from natural numbers for ordinary computability to sets of natural numbers to encode things a little bit more refined encoding of what was going on in lambda calculus.
And in particular, then, you were interested in looking into those notions in the presence of recursion with higher types. Is that the idea?
So the recursion in higher types, again, there was kind of technical development of Kleene model that was involved, and finding the right way to formalize the question, and then finding the right inductive argument. In this field, and in the programming side of computer science, the theoretical sides of programming, everything comes down to finding the right inductive argument. And I had a crisis point when writing my PhD thesis that it all hinged on finding a particular inductive argument. And so setting up that inductive argument was the big key that I had to solve in order to get a thesis out of it. And so I tried to teach my students this. It turns out that inductive arguments are not natural and obvious to students who are being taught about the theory of programming languages. Teaching how to do an inductive argument is very hard, and people are taught induction over the natural numbers, which is a relatively simple special case. But if you're writing a PhD thesis, you have an induction over some hairy stuff, and getting it all to fit together is often non-trivial.
So, sorry, I think you lost me a little bit. So you're saying that the inductive argument was the higher types thing?
In my thesis, I can't remember the details of that particular inductive argument, but
right.
It was the key challenge. Was you have some kind of structure that's in your model, and you have to prove something about it. And you prove that by induction, and setting up the induction, and usually the induction is over multiple factors, and so it's some kind of hairy, well-founded partial ordering.
There is a running joke on the theorem proving community where, by the mathematicians, that they say that all we do is induction over some data type. That's all our proofs are about.
Well, any in this particular area, computability or programming language theory, it's basically all induction.
Yeah,
and so there's a classification. If some undergraduate, smart undergraduate student is destined to go on to graduate school and do research in programming languages, at least the foundations or theory of programming languages, the essential ability they have to develop is to do inductive arguments.
Yep.
And so students who don't get induction are not going to go on to graduate school in this area.
That is a fair assessment. Well, how about we change gears and we start talking a little bit about LCF and ML. What is the story there? How did you get involved?
Right. So back to Dana Scott again. In the late 60s, he was looking for this mathematical model of the lambda calculus. And the tricky thing there is that the lambda calculus is about functions. It's a notation for defining functions, but it allows for functions to be applied to themselves, sort of self-application of functions. Lambda x x x is the typical example, a function that takes an x and applies it to itself. Right. So that implies, first of all, that everything is a function because you're applying x to itself. It could be anything. And also that a function can be applied to itself. And so that's kind of a mind-blowing notion. And so that was the difficulty in finding conventional mathematical models. So I mentioned this field of model theory, which is you take a theory, a bunch of axioms in, say, first-order predicate calculus, and you say, what is the mathematical structure that models this bunch of axioms? And then, of course, if you can prove a theorem from those axioms, that theorem will be true in the model as well. That's the whole thing. Deduction is a valid way of proving things that are true. But a true meaning true in a model or all models of a theory. So it's a natural question to ask of a formalism like the lambda calculus, which was originally partly thought of as a logic. So what's a model of the lambda calculus? And so Dana Scott attacked this problem in the late 60s, and he found it difficult, and he couldn't come up with a model. And so at that point he said, well, maybe I can't find a model, but maybe I can still do a logical theory about functions, computable functions defined in the lambda calculus and other formalisms. So he came up with a logic for reasoning about computable functions called logic for computable functions, or LCF. And so it's a bunch of axioms, and the proofs would typically be inductive proofs, but they would be based on this particular theory. And so he wrote a paper about this. I think the title of the paper is I Swim, Cooch, and What You Will. I Swim is Peter Landin's kind of formulation of the lambda calculus as a programming language. And Cooch stands for Curry Church, which is a combination of Curry and Church's idea about computability via the lambda calculus or combinatory logic, etc. And he gave in that paper, which was kind of distributed informally but not published. But then, inspired, as I mentioned before, by Richard Platek's thesis, he actually discovered a model. And so because he had complained about not being able to come up with a model in this paper on the LCF logic, he didn't publish that, and he kind of attempted to suppress it. I have a copy, but you have to know somebody to get a copy. And instead went and developed domain theory. And where am I going? So
we're headed towards ML.
Right. But so Robin Milner was interested in proving things, practically speaking, and using software in the form of some sort of proof assistant that could do some of the boring or grinding work of formulating a proof and pushing through a proof. So he wanted to take this Scott's LCF logic and implement a proof system around it, interactive proof assistant, which he also called LCF. So LCF became a proof system at that point. And he worked on that at Stanford during a visit around 1972. And then at that point he was writing the proof system in Lisp, and he was using Lisp as the kind of operating language or meta language for writing proof tactics and so on. And then he came to Edinburgh to take a position at Edinburgh, either the end of 72 or sometime early in 73. And at that point, he applied for funding for the LCF project, which was a kind of serious implementation of this proof assistant idea. And early on in that effort, with his first pair of postdocs who were working on that, which were Malcolm Newey and Lockwood Morris. Lockwood Morris was a student of John Reynolds at Syracuse, and they came to work with Milner at Edinburgh. So they started developing this LCF system, and instead of Lisp, which was, the problem was if you had a bug in your meta code that was sort of kind of driving the proof process, that would allow you to come up with invalid proofs, which was a bad thing. So he wanted a more secure meta language for driving the proof process. And so he decided to use a variant of ISWIM with type checking added. So ISWIM, you have to back up a little bit to Peter Landon. So Peter Landon was a brilliant guy who came out of, well, he didn't have a PhD, but he worked with Christopher Strachey. So Christopher Strachey is, so there's Turing and then Christopher Strachey. Turing is generation 0. Christopher Strachey was a young student who worked for a while at Manchester with Turing, but became a kind of a big software guy in the 1950s and into the 60s. So Christopher Strachey founded a kind of consultancy company in London in the 1960s, and he hired Peter Landon. And Peter Landon was entranced with the lambda calculus, and so he thought there were various ways you could use the lambda calculus. One, you could make it into a programming language by adding some more conventional symbolism, syntactic sugar, he called it, and that he defined a language called ISWIM. He didn't implement it, but he wrote several papers using ISWIM, describing a kind of operational model of it, kind of abstract machine. And he used it as a semantic model for Algol 60, so a way of defining Algol 60 by mapping it into the lambda calculus, and so on. So he wrote a series of 4 or 5 papers in the mid-60s that all came out around 64 to 66 that are extremely important. The one that describes this ISWIM language is the next 700 programming languages, basically saying you can get whatever programming language features you want by just sort of modeling them in this lambda calculus-based language. And so Landon's work was, Landon, partly learned what was going on from Christopher Strachey, and Strachey went on to take a professor's position at Oxford, and then he hired Rod Burstall, who was my boss at Edinburgh. So Rod Burstall worked with Strachey and Landon in London. There's a neat story here about how a bunch of computer scientists at the very beginning of sort of British computer science got together. There was a guy named Norman Pragnell, who was an amateur mathematician. And he was interested in kind of weird fringe ideas in mathematics like combinatorial logic and the lambda calculus and that sort of thing. And he started a kind of reading club or what he called a seminar. And he would use a kind of borrowed classroom. He knew a janitor or something at Birkbeck College in London, which was part of the University of London at the time, who could allow him access to a classroom out of hours. And so he would find people and invite them to his seminar. For instance, Rod Burstall he encountered at Foyle's bookstore. Rod was in the mathematics section looking at a book on combinatorial logic, probably Curry and Fraze, volume 1 or something. And so he invited him to his seminar. He found Peter Landon in the city library in Sheffield, and he noticed that he was reading Principia Mathematica. And so he invited Peter Landon to his seminar. And I think Robin Milner, maybe Tony Hoare, I'm not sure exactly who attended these seminars, but a bunch of important people who became important, met each other and got to know some of these weird ideas at Norman Pragnell's informal seminar. So that's a very British thing, the sort of idea of amateurism. And I think none of these people, Burstall got a PhD in operational research, but I don't think Strachey or Landon or Burstall, or Milner, none of those had PhDs. Turing got a PhD, but kind of as an accident, he was sent by his mentor at Cambridge, Max Newman, to go study with Church, where he did a PhD in a year and a half or something. But PhD wasn't necessary. There are people at Cambridge. Turing was a fellow at King's College, Cambridge. So becoming a fellow meant that you did well in your exams and produced interesting stuff, and then you'd be invited to be a fellow and part of the teaching staff at a college. So that was true of Strachey and Milner as well. I think Milner was teaching at a secondary school somewhere near London.
Wow.
And then got a kind of research assistant position at Swansea University, and then went to Stanford, and then came to Edinburgh.
So you were saying that Milner saw, I think it was done as called LCF, and implemented that logic as a programming language. Was that the idea?
No, he implemented so when you have a theorem proving system, you're trying to prove theorems, and you are proving theorems in some logic.
Yep.
And so the fundamental logic is things like the predicate calculus, just logical connectives like and or and not, and then quantification, universal existential quantification, and so on. And that's the language in which you write your propositions or theorems.
Right.
And you want to prove them, so you prove them using some set of axioms, basic statements, and the inference rules. The logic is sort of how you go from one proposition to another, or how do you infer results. And so the theorem proving system is meant to produce proofs. And the programming part of it is automating that process of producing proofs. So the automation is taken care of by providing a language in which you write what they called tactics, or to like in a particular form of induction might be a fancy tactic.
Mm-hmm. So let's see if I got this right. So Milner wanted to make a language for proving things, right?
Well, no, Scott, he found it on the shelf because Scott had written this paper, and Milner had gotten a whole copy of this paper that wasn't published, but was circulated. And he learned about this particular logic that had special features for reasoning about computable functions.
Right. And is that how ML came to be? Was by
Well, ML was the automation part.
Right.
So the proof part you could do by hand, and then normally, classically, all that would be done by hand with a bunch of hand waving, details left to the reader. And so, but you can make mistakes in the hand waving or the pencil and paper development of the proof. So automation was desired to reduce the amount of work and guarantee validity, make sure you didn't make any logical mistakes in your proof. So you could trust that if your proof system could produce a result, a consequence of the theory, you would know that that consequence was a valid, logically valid consequence of the theory because of some guardrails that prevented you from making mistakes. And so, but the process of putting things together, choosing what kind of inference step to use, setting up the framework of a proof, etc., was something that could be automated. And as I mentioned, at Stanford, the first generation of the LCF prover was written in Lisp, and so you'd write Lisp code to do the automation, and Lisp code could have bugs in it that would cause invalid reasoning. So to prevent invalid reasoning, ML replaced Lisp, and the magic that would make it more secure for this purpose was to have a type checker, a type system and a type checker.
Right.
So that's what Landon's ISWIM and, of course, Church's lambda calculus didn't have a type system. It was everything was untyped. Church in 1940 wrote a paper called A Simple Theory of Types, or maybe a theory of simple types, I don't know. Anyway, where he added a basic type system to the lambda calculus. He was thinking of that kind of as a logic at that point in 1940. And so in this case, the programming language, the kind of ISWIM-like language, was not itself the logic. The logic was a separate thing, these axioms of the LCF theory. And the automation was done in the programming language that they called ML for meta-language, because the logic per se and the things that you dealt with, formulas and propositions and theorems and so on, that was the object language. That was the thing you were operating on and generating proofs. Although, in fact, the LCF system didn't generate proofs as such. It produced a theorem and said this is a valid theorem, and didn't construct a proof. So there's no proof object. Some theorem-proving systems produce a proof, and some don't.
So it throws away the proof, that's the idea?
Effectively, yeah. You could have some kind of trace of the computation that produced the proof, and you could view that as a proof or try to transform it into a more conventional human-readable proof. Or you could just say, I trust this system is correct, and if it says it's a theorem, it's a theorem.
So it's fair to assume that Robin Milner never expected ML to be so big as it is nowadays.
Right. So there's a special purpose language to be used as the meta language for this particular proof system based on the LCF logic. And its properties, namely the type system in particular, were to provide security or the guarantee that when it computed a theorem, it was a theorem. That it was logically derivable from the LCF theory.
Right. But it seems like the community liked it and it gained traction somehow. What is the story there?
So what happened next? Well, they wrote this book on the LCF system, which included as part of it and the whole thing was written in Lisp, including the implementation of the ML meta language, which is a kind of integrated component of the system. And chapter 2 of the LCF book described the meta language. That described the original version of ML, which we tend to call LCF/ML, the original LCF ML. And a couple things happened toward the end of the 70s or early 80s. Rod Burstel and I decided to do a functional language we called Hope. And this was a different style. It wasn't lambda calculus style, but we borrowed the type system and added some new ideas. But so the type inference, the type checking and type inference, so as a programming language, probably the most interesting thing about ML in the LCF formulation was that it had a type checker. It had a type system, types, and which are some kind of formalism for describing the workings of a function. And it had a type checker that would statically detect errors in the typing of a program. And that type checker went beyond just type checking. It derived or inferred typings. So it could leave the types out of the original program, and it would infer what the types need to be. And this inference was based on augmenting the type system with polymorphic types, which is parametric types, more flexible types, like the type of the identity is alpha arrow alpha, where alpha is a kind of universally quantified type variable. And so these polymorphic types were kind of integral to the way the type inference worked. And Robin discovered this and incorporated it into the LCF ML design. And in terms of language, that was a huge innovation. But it turned out wasn't quite as innovative as originally thought, because it turns out that on the logic side, Roger Hindley, who's at, I think, Swansea, had written a paper in, sometime in the 60s, describing essentially a similar type inference algorithm, which was based on an earlier paper by Curry in the late 50s, describing such an inference system, which was kind of an echo of something Curry had kind of hinted at in his first paper on functionalities or types for the combinatory logic that he had developed in his PhD thesis at Gothenburg.
Princeton?
No, Hilbert's University in Germany.
Oh, okay.
Göttingen. Anyway, Curry went to Germany to do his PhD thesis with
Church.
Not Church. Church was at Princeton. So he didn't need to go to Germany to work with Church. He went to Germany to work with Paul Bernays.
Oh, I thought he did his PhD with Church. With Church.
Well, it's always possible that he studied with Church before, and European and American PhDs are sometimes kind of incomparable, and you could get both. And anyway, did get a degree, a PhD at Göttingen with Paul Bernays, and that was combinatorial logic.
Right.
But in 1934, he wrote another paper where he talked about essentially types for combinatorial logic, which he called functionalities.
Gotcha.
Anyway, and he came back to that in the late 1950s and wrote up a description of type inference for these functionalities for combinatorial logic. And turns out that actually in 1943, Max Newman, Turing's mentor at Cambridge, and later on a prominent person at Bletchley Park in the code breaking world, and then the head of the computing lab at Manchester after the war. So Max Newman wrote a paper in 1943 about typing initially Quine's new foundations, which is a kind of a different formulation of logic. But he also essentially, as a side light, gave a type inference algorithm for the lambda calculus. So there was a line of work related to type inference on the logic side that no one was not aware of until later. And so it was an independent rediscovery in the LCF system.
We have this saying in computer science that any good result in computer science is usually going to be discovered 3 times, right? First in logic, then in math, and then in computer science. It's kind of the same thing.
Logic is part of math.
Right.
At least logicians consider it part of math. It depends. Often in a math, logicians in a math department are viewed as a kind of strange side. But back to ML as a programming language. So it had this great magic trick, which is type inference and polymorphic types. And that was attractive. And Luca Cardelli was a grad student at Edinburgh in the late 70s, got his PhD in 81, I think. He decided he'd implement ML as a programming language, a freestanding programming language. So he wrote an ML compiler in Pascal, generating VAX machine language, and he introduced several language innovations in his version of ML, and we tend to call that Cardelli ML. And there's a paper, I wrote a paper about that at some point for a kind of Cardelli Festschrift at Microsoft. And so Cardelli ML was the first, I should mention there was a language developed at MIT in the mid-60s called PAL, P-A-L. And this, Landon spent some time at MIT in the 60s. He left Britain, he went and worked at, I think, Univac in New York City, but sometime during his time in the US, he spent a few months at MIT, and he obviously taught them about ISWIM, his lambda calculus-based programming language. And 2 professors at MIT, I don't know whether they were professors at the time, Evans and Wozencraft, implemented this PAL language. So the PAL language in the 1960s was the first implementation of ISWIM, but that, I believe, is not typed. So anyway, Cardelli's compiler was the first implementation of ML as a separate freestanding programming language. And then what happened was that Cardelli, after he got his degree from Edinburgh, came to Bell Labs, where I was working at that time. And shortly after he arrived, we started working on something called Standard ML, which is another story. And so Cardelli ML was modified gradually to be mostly Standard ML compatible.
Mm. Okay, so Standard ML is completely separate from Cardelli ML.
Not completely separate in the sense that, so what happened with, so we had LCF ML,
Right.
which was used by people using the LCF theorem prover system. It wasn't intended to support programming by itself. It was only used to program proofs and proof tactics in support of automation of proofs in LCF. But there were a couple offshoots of that. There was Cambridge LCF. Larry Paulson and Guy Cousineau from INRIA worked on that. And then there was a Chalmers LCF, a group at Chalmers University in Sweden, in Gothenburg. And at least Cambridge ML, I'm not sure about the Swedish version, made some slight changes to the language for more power and convenience or something. And meanwhile, Rod Burson and I were working on this Hope language at Edinburgh, which was another kind of cousin of ML, because we adopted essentially the same type system. And the main new thing that Hope introduced was algebraic datatypes. Idea of a data type that could be parametric and recursive, but was defined by a set of constructors for a type and so on. So we call that algebraic data types. And so there were these several things happening where there was a possibility that there would be duplicated effort and divergence and so on. So a number of people in the British computer science establishment, a small group in the British computer science establishment, decided that maybe these parallel efforts should be coordinated or unified. And so there's a meeting in the fall of, I think it was 82, where the establishment, a few of the establishment figures, including Robin Milner, came together and discussed the future of ML as a programming language. And there was, I believe, some funding that derived from that. And so back in Edinburgh, Robin wrote out a sketch of a kind of standardized ML that would bring these parallel things together, in particular Hope and the ML dialects. And so that he called the thing standard ML because it standardized these independent parallel efforts.
So that then they included the notion of data types into standard ML.
Say that again.
What I was asking was, so you said that standard ML took all of the different approaches of functional programming that was happening, like ML and Hope. So my question was if that's when standard ML also got the notion of algebraic data types from Hope.
Right. I forgot to mention, I should have mentioned that Cardelli ML was another of these dialects that was branching off.
Gotcha.
Because Cardelli introduced several new and interesting ideas in terms of the type system and the syntax of the language. So on records and unions in particular. So the original LCF ML had pairs. It basically had rather limited data structuring tools. Basically had binary pairing, which could be nested to produce triples and quadruples and so on.
Right.
But it didn't have, and it also had a kind of raw union. You could have type 1 plus type 2. Okay. And so you could have a binary discriminated union of two types. And then you could inject T1 into T1 plus 2T, or you could inject T2 into T1 plus T2, and you could project them out of the union and so on, and you could test which component of the union you had. And that
so there was already a notion of pattern matching in that sense.
Well, there wasn't really support for pattern matching.
For plus.
It was just construction and an interface of operations for manipulating values of a union type or producing values of a union type. But pattern matching was not provided. There was rudimentary pattern matching over tuples. These were originally called var structs, the patterns. So the var structs were restricted to basically variables and tuples of variables, like x, comma, y.
Okay.
And var structs were kind of in Landon's original ISWIM as well. So there's very limited, very rudimentary pattern matching.
Yep. Yes.
That didn't do a discrimination over cases. So Cardelli had kind of beefed up the union type to, you can go from tuples, you can go from pairs to n tuples, and similarly and then you can go to records where you have named fields, which is a kind of variant on tuples. And Cardelli, in parallel, produced kind of labeled unions. So you could have labeled components of unions, which were sort of like the constructors of data types, algebraic data types. So that's, but he didn't, I don't think he had a pattern matching over union. So anyway, but there were these new ideas and he also had some new kind of combinators for combining declarations that were interesting. And, as I said, there is a paper about Cardelli's ML, its influence.
I'll definitely link that in the description of the episode. So let's talk about Hope. What do you guys think? So you were working with Burstall at this time, and then you started working on Hope. What were the thoughts over there?
So I should say a little bit more about what Edinburgh was like. So Edinburgh was a great place because it was where things were happening, and people came to visit, like John Reynolds, Bob Constable, the INRIA people. It was kind of a center, a European center of active development of ideas in formalization of programming and programming languages. So it's a good place to be. But the Edinburgh community was split into two parts. There was Robin Milner's group, and he was in the computer science department, which was in a kind of separate campus 3 miles south of the main campus, in the sort of engineering campus on what's called King's Buildings. And Rod Burstall, the part of the School of Artificial Intelligence that we were in, that is Burstall and Gordon Plotkin and some other people, was, as I said, part of the School of Artificial Intelligence, and we were housed in an old building called Hope Park Square. And that's where the name Hope came for the programming language. And there was 3 miles difference, 3 miles distance between these two locations. And so we didn't really see each other casually on a daily basis. Sometimes you'd get on the bus and go down to King's Buildings, but usually not. So they had an institution called the Bob Boyer Memorial Society. So Bob Boyer and Moore developed this theorem prover, which became the CLA, I think, theorem prover, computational logic or whatever. They had left Edinburgh by the time I got there in 1975, but kind of as some kind of tribute to Bob Boyer as a unifier, we had this Bob Boyer Memorial Society, which was a seminar bi-weekly or every other week. We would meet at somebody's home and have a seminar. Typically, a lot of the meetings were at either Rod Burchell's home or Robin Milner's home, because everybody else was in rather small flats. And this is how we found out what the other side was doing.
Mm-hmm.
And that was the kind of unifying factor at Edinburgh, the Bob Boyer Memorial Society. Anyway, but eventually, toward the end of '79, the Burstall Plotkin group moved down to King's Buildings and joined Milner, and then a few years later they established something called the Laboratory for Foundations of Computing, LFCS, which was in the computer science department. And then much later, the computer science department joined the rest of the AI department and so on in a new informatics division in new buildings in the central campus area. So that's, if you go to Edinburgh these days, you'll go to the informatics division in its building near the central campus. Anyway, so what happened is in 83, it just so Robin wrote this sketch of the language, and he gave it a name, Standard ML, to kind of represent the fact that it was trying to bring these different parallel things together. And it so happened that I was in Edinburgh. I came back to Edinburgh every year during that period, and Luca Cardelli was there. I think Larry Paulson from Cambridge was there, and Rod Burstall and Robin Milner were there, and so the Edinburgh people were there, and a few of the outsiders, and I think Guy Cousineau from Gerard Ouette's research group at INRIA was there. And so we spent most of a week, at least several days, discussing Robin's proposal, that first draft of Standard ML. And then there was a flurry of correspondence. People left, and in a couple, 3 months after that, there was a bunch of correspondence about this. And then there was a second meeting a year later in the spring of '84, where these discussions continued. And then there was a bit larger and more formal meeting in the spring or June of '85, which tended to fill in more of the details. And then by the end of 1985, there was a tech report that informally described the language, called Standard ML. So it was kind of three meetings and a bunch of correspondence in the period 1983 to 85, 86. After that, in '85, Bob Harper came to Edinburgh as a postdoc and initially worked on Standard ML. And there was this tech report, informal description, and then Mess Tofte arrived as a graduate student, and he worked on the formal specification, the formal definition of Standard ML, which was published as a book at MIT Press.
So the original question was, what's the story of Hope? What are you guys thinking about?
Well, so Rod Burstall had been doing work on program transformation, and the language the programs were written in for purposes of transformation and improvement. So the idea was you'd write a kind of almost algebraic specification, a set of equations defining some functions, and then you'd massage those functions using various transformation techniques and come up with something that was more efficient. So the initial set of descriptions of an algorithm were very much like a specification, a set of equations. And through these manipulations, you turn that into a more efficient program. So there's an idea of a kind of formalized, potentially automatable way of generating programs from specifications. And the language that was based on was essentially just first-order recursive equations defining functions. It's rather like the original computable function description that Gödel came up with in around 1930 or just before 1930, which was called general recursive equations. And it was first order. There was no lambda term that could denote a function in itself. And he wrote some papers with John Darlington on this transformational program development project. And then later on, he thought about adding types to this same language. And he came up with a scheme that he called NPL, which stood for New Programming Language. And that was only described in a rather obscure paper that was published in some industrial conference in Japan. So that didn't get very wide publication. But this idea you'd introduce a type, and then you'd introduce constructors for that type, which you could think of as just uninterpreted function symbols. So you had these equations which defined functions that were defined or derived, and then you'd have these other function symbols whose type was specified, and they were associated with a particular producing a particular type. So, for instance, you might introduce the list type, and these could be parameterized. So you might introduce the list type with one parameter, and then you could define. Then, first of all, you define constructors nil and cons, and give their types. Like nil would be of type alpha list or something, because there was. I think probably from the beginning there was a notion of polymorphism here, because this was developed when LCF had been launched, and we were familiar with the ideas of LCF and ML, and then you'd write a bunch of equations that defined other functions like append or something. But the type part would be described by introducing a type, the name of a type or type constructor like list or bool. So bool would be a simple example where you'd introduce bool as the name of a type, and then you'd say there's true, which is one constructor, and there's false, which is another constructor. And then you could define equations defining not and or, etc. So that's basically, and then so the equations were like these first order equations from the previous language for the transformation work, but the type stuff was new, and he didn't implement this language. He described it informally in this one paper, but starting from that, Rod and I developed the Hope language, kind of scaling it up into a real language. And the interesting about this NPL was that you could keep adding new constructors, and then you could keep adding new functions. So if you defined a new constructor for bool, you might say true, false, and foo. And now you could define how your functions operated on the foo variant. And so it was a kind of implicit tagged unions, but they were extensible in the sense that you could go ahead and continue defining new constructors. And once you define new constructors, you could define new equations defining your functions over those new constructors.
Yes, but that sounds very sounds a little dangerous, right? Because then your functions have to be kind of open.
Exactly. So the types were open, to extension with new constructors, but the functions had to be open as well,
right,
to new defining equations. Interesting, and it wasn't developed very far as a language in its own right. It basically was the starting point for Hope. And one of the things, of course, that Hope did was close these things off, so that when you define the type and the constructors, that was a kind of closed thing, and it wasn't open to extension. But the idea keeps popping up again because it's something that is useful in certain circumstances to add something to a union type.
Yes. And then I also see a lot that the original idea for these constructors and then data types is the notion of free algebras. But how does that come about? What is the idea there?
Well, yeah, so free algebras is basically, it's a mathematical notion kind of generalizing the notion of a algebra which has a carrier set and then operations like a group or a ring or whatever. And a free algebra is where you have some operations on the algebra, but you don't define them. They don't. There's no computation or reduction or simplification available. So if you say have function symbols f and g and a, and say a is just an individual, you can, and maybe g is a binary function and f is a unary function. You can say f of a and f of a and g of f of a and f of a and blah, blah, blah.
Right.
So you can generate terms using this little language, but the terms don't compute something. They just sit there, and they may represent something. So free algebra is just you give some constants and operators and you build terms out of those things, but the terms just... this is related to the notion of the Herbrand universe in logic. Just saying, I'll give you this alphabet and you can compose terms over this alphabet, but there's nothing going on. They just sit there. And that's what data types are.
Yes. And this is really cool because I'm not sure if the listener noticed this, but it just explain why algebraic data types is called algebraic to begin with, right? It's because of they are free algebras, right? And that was the original idea driving the... As a mathematician, yes. As somebody trained as a mathematician, this kind of terminology was familiar to me. Right. And it's kind of lost. Like my generation of academics, we don't have access to these ideas so easily these days. So we're kind of like, oh yeah, algebraic data types. We all know what that is. Like whatever.
Yeah, and this is somewhat characteristic of a difference between European and American computer science culture. So in Europe, theoretical computer science developed in a different direction from American. So in American computer science, the theoretical side was about complexity theory and algorithm analysis and measuring the cost of things. And the underlying related mathematical field is combinatorics, counting stuff in complicated ways. And so in Europe, a large part of theoretical computer science was about reasoning, trying to logically capture the meaning of things and to reason about them, reasoning about the correctness of programs or reasoning about the logical models for language, the semantics of the language. And so this is stuff that's connected to logic and to some extent to algebra, because they were kind of algebraic flavored approaches. And so there's a pretty close connection between the development of computer science and theoretical computer science in particular in Europe and programming and programming languages. Whereas in the US, programming language is considered part of systems. You just hack a compiler.
Yep.
You invent a programming language by hacking a compiler for it, and you don't worry about the definition. Until maybe years later, there's some kind of standards body that writes 10,000 pages of code, of prose about it.
Yep.
Anyway, so obviously the combinatoric theory, the combinatorics-based theory in the U.S. is relevant to the invention of clever algorithms and so on, which can be useful in practice. But in terms of informing how to program, it's not very useful.
I really like when you mention that the notion of algebraic data types itself came from this idea of generating code from specification. And I think that is very cool from a programming perspective. And I think it's a theme that is still alive. It's even more alive nowadays, right? Like with kind of like lightweight formal methods research that we're having these days with like liquid types and that sort of ideas. Like how can we reduce the burden of generating correct by construction code? And it's very interesting to me to see how in the dawn of something as prevalent nowadays as algebraic data types was the same idea of like, how can we guarantee that we're generating code from the specification correctly?
Right. That was clearly a primary motivation of the program development by program transformation work that Rod Burstall and John Darlington were doing. And it was kind of connected with the context, which was that this was being done in the School of Artificial Intelligence. So there was a kind of interesting intellectual connection between programming language and programming semantics and so on, the theory of programming, and work being done in parallel at the time in artificial intelligence. And there's an important series of meetings, kind of summer meetings, summer conferences at Furbush, which was a little resort on Loch Tay, north of Edinburgh. During the summers, this is before my time at Edinburgh, but there are several volumes of kind of proceedings of the Furbush summer schools, which contain an interesting mixture of artificial intelligence papers and programming language related papers. Like people like Rod Burstall contributed to those meetings. And there was, when I got to Edinburgh, there were some interesting AI programming languages that I studied, getting into the field, like Planner and Conniver. Those were languages that essentially had some kind of built-in search feature. QA4, Planner, Conniver, QA4, and these are languages that, there are people like Richard Waldinger involved in one of these and came out of MIT and Stanford and so on. And so those were taken seriously as part of the field of programming languages. And Prolog, which was developed in France and then in Edinburgh by Kowalski, is another language that had a kind of built-in search capability. And the pattern matching in ML is a kind of half of what you have in Prolog.
In what sense? What do you mean?
It's a one-way pattern match. I mean, you compute a value and then you match it against the pattern and bind some variables, whereas in Prolog you're doing some kind of unification like process across two partially defined things. So the patterns and the values are more mixed.
I see. There is
so pattern matching in ML is quite straightforward,
right.
But efficient compilation is an interesting problem.
Yes, part of my master's was related to that, and yes, it's an interesting literature there for sure. There in our notes, you also included something along the lines of type constructor equivalence and equality theory to generate type declarations. What is this about?
Well, when you think about the problem of type checking, it's a large element of type checking is taking two types and then seeing if they're the same or equivalent in some sense,
right.
whether two types match. And when you get into an interesting type system that has things like type functions, so in ML, the data type constructors are sort of like the constructors of a free algebra. They don't reduce.
Yep.
They don't simplify. But there are other type constructors which are defined, like pair of alpha is equal to alpha cross alpha, something like that. So there's a little functional language in the type system. And because of this little functional language where you have defined operators, those operators can reduce or simplify. And that reduction process comes into play when you try to compare two types. You kind of eliminate the defined types to get down into some ground form where you can just compare things structurally. So there's a very, but it's all first order and quite simple. Anyway, in general, in type systems, there's a huge literature of type systems with many additional concepts that you can introduce. Obviously, recursion, existential and universal quantification, et cetera, et cetera. And, Benjamin Pierce's book on type systems for programming languages summarizes most of these things.
Yes.
Most of the basic things.
Yes, absolutely.
Anyway, so for practical purposes in a programming language, you want the type equivalence problem not to be too complicated, because the type checker is solving that equivalence problem everywhere, all the time. So that's one of the things, and there was one problem that came up because way back in 1973, what's his name? It's in the notes, but there was a guy who wrote a paper in the first POPL conference about the problem that kind of amounted to, what if we have recursive type operators and we want to build type terms using these recursive typed operators, like list is a typical example of a recursive type operator. So you want to take two terms that involve these recursive type operators and tell whether they're equivalent. And turned out this was equivalent to some automata theoretic equivalence problem for deterministic push-down automata or something. Solomon, was it Solomon? I think it was Solomon was the author of that paper. And so this is a kind of known result that this particular equivalence problem with recursively defined operators was an open problem at the time. It turned out many years later to be solved, and it turns out to be possible to solve that equivalence problem. But obviously, the fact that it took many years to discover that means that solving that equivalence problem is non-trivial. And So that'd be a complicated, messy part of your type checker if you tried to do that. So, we wanted a language with recursively defined type operators, like lists. That difficulty was related to kind of direct recursion, or what one would call equirecursion. That T is equal to mu alpha dot T prime or something, where you have you can have a notion of recursion which is kind of direct and can be unwound wherever you feel like unwinding it. And then the question is, where do you unwind it and where do you wind it up? And how many times, and so on. That's why it's hard. So this simple version of equirecursion, where a type is just directly defined recursively in itself, leads to at least algorithmic difficulties in your type checker, and at that time, unknown theoretical issues, and unsolved theoretical issues. So you can get away from that by using what we know as iso-recursive types. So it turned out that, the recursive types in ML, let's go back to the LCF ML, the original version of ML. The definition of something like list was through the notion of an abstract type. Okay, so it had an abs type construct in the language that you could use to define new types that could be recursive. And this was, I'm not absolutely sure, I never asked Robin directly whether this was derived from CLU, because CLU clusters have essentially the same capability.
CLU is another language?
CLU is a language that was developed by Barbara Liskov at MIT in the early 70s, like 72, 73, something like that. And early to mid 70s, there was a lot of interest in the problem of abstract types and designing languages that supported abstract types. The idea being you have a type and it has some representation, has some data structure, but you hide the representation and provide only a restricted, well-defined interface to operate on that type, instead of manipulating the representation directly. So there was CLU and the Alphard, which were the most well-known full language. Alphard came out of CMU, and I don't know whether it was ever implemented. CLU was implemented by Liskov's group at MIT, and there's a book on CLU. But it also had an abs type. So it appears to me, although I can't confirm this because Robin is gone, that the abs type notion that's built into the LCFML was at least inspired by the CLU abs type or CLU cluster notion. And I think Alphard was also, in that same complex of ideas around the same time. So the idea there was that you had the type itself and you had its hidden representation. And to manipulate, you had, if you had one of the values of the abstract type, you wanted to make it more concrete by turning it into, being given access to its representation as a data structure. And so there was a rep mapping that mapped the abstract value to its representation value. And then the representation value is something concrete, like a bunch of tuples or something that you could operate on.
How would you implement lists with this idea?
Well, you'd say that a list is the representation of a list is a tagged union of a nil case and a cons case, and a cons case has a pair. And actually, Landon, in his writings on ISWIM in the 1960s, had an informal way of describing types that was not part of the language. It was kind of meta language, where he could say, an expression is an atomic, or that had a symbol, or it could be an application that had a radar and a rand, and operator and operand, and so on. So it essentially said, I've got this kind of abstract notion of an expression, and it's represented in terms of a tagged union of this and that, and so on, and tuples and whatever. But for Landon, that was just kind of a meta description. It wasn't part of the language.
Gotcha. I thought it would describe it abstractly. That's why I was having a hard time, because if it's just abstract, how would you define the tagged union, nil and cons, right?
Right. So the tagged union of nil and cons was on the representation side. And if you had a list, you'd have to turn it into such a value by applying the rep or representation function to get to its concrete representation. Then you'd manipulate that. But then you want to go back to the abstract version. So there's an abs that maps back the other way.
But then
and
your
the rep and the abs are two halves of a isomorphism.
But then your function has to be implemented in terms of the concrete, not the abstract.
Right. Mm-hmm. So your append operation, this is in old LCF ML, you define, say, append on the in the sort of body of the abs type thing as an operation that operated on the representation. Mm-hmm. And then you'd map things back using the abs thing. So
is this by the time another point of our notes here is that this is when we're building the semantics of types and how recursive types was kind of an issue at this moment?
Well, it's more like a historical thing that this is the way recursive types were done earlier. They were introduced. Later on, there were type theories and type systems and so on with these more abstract constructs like the mu operator that built a recursive type term that could be manipulated according to various rules. But before that, there was this more pragmatic and concrete way of doing things in clue clusters, and then the abs type declaration in LCF ML.
Right.
And so once we had algebraic data types, when we went to standard ML, most of the uses of abstract data types to define something like lists, the list type operator, we didn't need the abs types for that anymore because we could. That was kind of achieved by the algebraic data type thing that could be recursive. But in the algebraic data type thing, the abs and rep were still there, but the abs was basically the constructor as constructor, like cons, actually constructing a list. And the rep mapping was the pattern matching aspect of the constructor. So if we wanted to break up a list that happened to be a cons, we would match it against the cons pattern. And of course, distinguish between the nil and cons case would be done by some kind of case construct.
Yes.
So pattern matching, you have constructor side and destructor side, which is the pattern matching.
Right. And which arises very naturally when you start thinking on those terms. And it's absolutely beautiful because, it's one of the main features that we expect from having what we call the functional programming languages nowadays is a proper implementation of algebraic data types, which we started seeing in more mainstream languages such as Rust and Scala these days, which is extremely exciting for us, I think.
Yeah, and then, of course, people say we could make this more powerful and interesting by going to generalized abstract algebraic data types or something.
Right, yes.
For me, that seems a bit too far because you lose the simplicity.
Yep, yes. And things start getting a little more complex on the implementation side, too.
Right. Yeah. I believe in simple things, simple languages, simple constructs, and so on. And also, there's the notion of magic. So,
right.
Prolog and these other AI languages from the 70s had a magic thing they did, which was their search capability. And that was useful but magical. It was hard to figure out in detail what was happening. And lazy functional languages have laziness as a part of their magic. And so...
makes things harder to reason about, right?
Yeah, I guess ML has type inference as part of its magic, but it's type inference seems to be worth the mystery.
Yes, I like that. So I think the next step of the journey here, I think we can start thinking of going towards the end of this first part of our conversation. It's almost 2 hours of conversation, but I think it's worth to start talking about SML and J. What do you think? Is that too long, or?
We can start.
Yeah.
Kind of background, interesting background is, so Robin was the initiator and kind of the intellectual leader of the group that got together and designed standard ML. And of course, Rod Burschel and I were involved, so the introduction of algebraic datatypes from Hope was kind of part of the initial plan. But there's a question, kind of unspoken question about where this was leading in the end. In other words, it was clear that we were going to design a programming language, but then the question is, what are you going to do with this design? You can publish a tech report describing the design. You can publish other papers about the type inference algorithm and so on. There is a 1978 Milner paper about type inference. And then beyond that, you can implement it so that people can actually use it as a programming language. And you can also formally define it. So Robin was particularly interested in the formal definition because that was a novel thing to do, is to design a language and formally define it as part of that process. And that ended up happening. And by the late 1980s, with Mess Tofta's PhD contributions and additional work on, formatting the rules, and it turned into a publication, a book that was published by MIT Press in 1990. So that left the question of what happens with implementation. Well, Robin, although he did participate in the implementation of the LCF system, and in particular the ML part of the LCF system, and I actually used his Lisp code for the type checker of LCF ML. And I still have a copy of that source code. He wasn't really thinking in terms of implementing standard ML. His kind of naive thought was they'd come up with this design, and then some commercial software house would be interested in writing a compiler for it. And that was quite unrealistic. So what actually happened is that, first of all, during the years when the design was actively being done, that is like 80, 83, 84, 85, 86, there was something called Edinburgh ML. So there was Cardelli ML, which was Cardelli's slightly improved dialect of ML with his own compiler, and that was a compiler running on the VAX, generating VAX code written in Pascal. And so Kevin Mitchell and Alan Mycroft did an effort to rewrite Cardelli ML in its own language. So they succeeded in doing that, and that became Edinburgh ML. So Edinburgh ML was essentially the same dialect of ML as Cardelli ML, but it had been re-implemented in its own language as opposed to self-implemented or reflectively implemented. I don't know what to call it. And that made it, in some sense, more accessible because Cardelli's Pascal code was idiosyncratic in certain ways. And I think, I don't know whether it was still generating VAX code or what, but I think it was still running on the VAX, which was a common architecture in the 1980s. There was also a DEC 10 in Edinburgh, which was the main machine used in the AI department, in the AI school. So we had Edinburgh ML, which was an ML implemented in ML, and it had a runtime system, garbage collector, and all that, and code generation. So during the standard ML design process, various people, Mitchell and Mycroft and Bob Harper later on, changed the Edinburgh ML into an approximate standard Edinburgh standard ML. So they basically migrated the language of that implementation to be close to standard ML, just to explore the feasibility of the implementation of features. And so there existed by the end of 1985, there existed this prototype-ish Edinburgh Standard ML implementation. And then also sometime during 85, David Matthews, who I think was at Cambridge at the time, he was interested in implementing a polymorphic language, and there was another alternative design called Russell. So Russell, presumably after Bertrand Russell, was designed by Donoghue and Demers at Cornell. And it's not clear to me that they ever had an implementation, but they wrote a paper describing this. And the interesting thing that gave Russell its power was that types were values. You could write programs that computed types. And they had some way of doing type checking, static type checking, which is a good trick. And so what Dave Matthews had done was he decided to do a serious implementation of this Russell language, or dialect of Russell, and he called it Poly, P-O-L-Y. So Matthews had a language called Poly, which was based on Russell and was implemented in itself. And he did that at Cambridge. And once descriptions of standard ML began to circulate, he wrote a different front end so that the Poly compiler could compile the standard ML language. And that came to be called PolyML, and it still exists. And so that was another implementation, in this case done by Dave Matthews, who was not part of the design group, but was doing his thing at... There was also another implementation because there was a fork in the design early on, probably 1984-ish, where one of the syntax design decisions in standard ML, so ISWIM had two forms of expression to combine a declaration with an expression, which would be the scope of the declaration. One was the let declaration in expression. It had another form, which was expression where declaration. So it had two forms doing the same thing, one of which had the declarations first and one of which had the declarations second. And when you're talking about a real programming language, it's a serious question about whether you want both of them, or if you only want one, which one do you want? And, for instance, say you have big 2-page declaration. You say, let 2 pages of declaration in some expression. Or you can have expression followed by where, followed by 2 pages of declarations. So reading the first is considered easier than reading the second, in the sense that when you're reading expression, you don't know which identifiers are defined in the where clause that follows. So you have to look ahead. So we decided to only have let and not do where. But people at INRIA thought that where was precious and necessary, and they were not willing to give it up. So they decided they had to take control of their own fate and do their own version of ML that had a where. And that led to something called CAML, because their implementation initially used some abstract machine scheme based on category theory, which was called the categorical abstract machine, or CAM.
So the only difference between CAML and SML is the where clause?
No. Unfortunately, there were lots of other minor syntactic, minor and annoying syntactic divergences.
Yes.
And of course, later on, the CAML group discovered their mistake and eliminated where, at least partially.
Right. Haskell didn't yet, though.
And standard ML eventually added back a different clause, used the where keyword in a different construct.
Really? What is it? What is that for?
That's for kind of post-modifying a signature. Say a signature has a type T, and the signature just says type T. And later on, you want a more specialized version where you say type T is int.
Gotcha.
And so you can have the signature S where type T equals int. That kind of, after the fact, defines the type component. Anyway, so CAML was implemented at INRIA, and a few years later, an object-oriented extension made it into OCaml. And then finally, I was sort of interested in implementing it, and Andrew Pell arrived as a fresh new assistant professor at Princeton in the winter of 1986. And we got together, and he was, I guess we discussed the idea of implementing standard ML, and he was keen to do it. And so we collaborated for 10 years after that, 9 years after that. So it would have been a different thing if I had implemented it myself, because not being a real computer scientist, I knew little or nothing about real compilers and things like code generation and runtime systems.
So just to make sure, so SML and J is the first implementation of SML. Is that correct?
Right. So SML or Standard ML of New Jersey, which is the full name, is a joke name, a pun, not a pun, but really a joke, in the sense that nobody understands these days. There used to be an oil company that was called Standard Oil of New Jersey. Standard Oil of New Jersey became Standard Oil, which was abbreviated to ESSO, which transformed into Exxon. So Exxon, a long time in the past, was called Standard Oil of New Jersey. And so we just substituted ML for oil.
And this is the first actual implementation of the standard ML. It's SML1J.
Right.
Okay.
So the idea was we would implement the definition of standard ML. And of course, when you've got a definition of a language, especially one that's attempting to be a quite precise, rigorous, formal definition, in principle, one should write an implementation that is a faithful and exact realization of that definition. But when one of the definers of the language, there is effectively a committee-designed language, and I was one of the designers of the language, and so when I did an implementation, I wasn't entirely happy faithfully implementing mistakes in the design. So there were a few divergences and some additions that were developed as part of Standard ML of New Jersey. And a little of that got incorporated into the revised language that happened in the 1997 or so, when a second edition of the book was published. And I'm currently thinking about, and there's been a couple things. There was a long design decision throughout most of the 1990s by a group under the heading ML 2000 or 2K, which could be 2048.
It's still going to get there. 24 more years.
Anyway, the ML 2000 discussions introduced a lot of interesting ideas and so on, and spin-offs, but they didn't really come up with a new, better ML, mainly because of the fundamental conflict over then popular object-oriented language design. Mm-hmm. Things like objects and in classes and inheritance and so on.
Well, at this point, I think we can stop here.
Yeah, this is enough for today, I guess. So.
Yes. So here's the background story about this episode. I was at Milan for ICFP 24, and I got this email from David telling me that he really enjoyed the interview with Satnam, and that they were friends for a long while. And in that episode, even him got to learn some stories from Satnam that he had never learned before. And he asked me if he could come and talk in the show too, because he said he felt like he had a lot to share. And to be completely honest, I wasn't sure who David was. It kind of rang the bell, especially because, you know, like I've actually worked with Hope Paper, like with the Paper of Hope. And when I put it on Google and I saw he was him, I was like, holy shit. That was so incredible. I felt so, it really gives me a lot of hope that we are achieving something relevant with this podcast. And I have a lot of plans for going forward in 2025, and really excited to share with you guys. Once I have a more concrete plan, I'll definitely share with you. So, well, guess what? This was actually the first half of the episode, and the second half will be released as soon as I finished editing. Actually, I have an editor, which is pretty cool. Helps me a lot. So in a couple of weeks, the part 2 of this episode is coming out. In the meanwhile, please make sure to follow us on Twitter, or should I say X? Nobody says X, but Twitter, at TT4All. And if you have any questions, any comments, please send us an email, typetheoryforall@gmail.com. And of course, don't forget to join our Discord. We are growing this amazing community of PL people. And As I said at the beginning, we are currently looking for study group leaders to organize some study sessions online in 2025. So see you guys in the next episode. Hope you guys have a great end of year festivities. Merry Christmas, and how's it for New Year? Have a great New Year. My English is broken today. Bye.